Good morning everyone. Welcome to the third lecture of our week number 2 where we are looking to finish off our module on the thermodynamic property relations. So, over the last two lectures we have developed the fundamental or generalized relations for changes in several thermodynamic properties or the thermodynamic properties which are of most importance to us, basically the specific internal energy, specific enthalpy, specific entropy and also two kinds of specific heats. Along with them we have also discussed about several important topics like different kinds of thermodynamic potentials, the concepts of Helmholtz free energy and Gibbs free energy are introduced. We have developed auxiliary relations such as the Mayer relation, which allows us to calculate the difference between the two specific heats for a given substance, and we have seen that depending upon the pressure and temperature level there may not be any difference between the two specific heats or there may be significant difference, but as a rule the specific heat corresponding to constant pressure, that is Cp, is always greater than Cv, or in the limiting case of absolute zero temperature or a purely incompressible fluid, that can be equal to Cv, but can never be less than Cv. We have also defined two new properties which you probably have not heard before that particular lecture, the isothermal compressibility and which is somewhat a way of representing the effect of pressure on specific volume, and also we have defined volume expansivity, which is a way of representing the effect of temperature on specific volume. So, both this isothermal compressibility and volume expansivity in a way is related to the PVT characteristic of a system, that is they relate the relation between these three fundamental parameters: pressure, volume, specific volume and temperature of a substance or a system. Just to have a quick recap, now these are the relations that we have developed for changes in specific internal energy and changes in specific enthalpy, and as is clearly seen from the relations, and also we have done one or two sample numerical problems using them. Here we just need to have two kinds of information. One is the PVT relationship for a given substance, which is actually known as the equation of state. So, the first thing that we need to know is the equation of state for the substance, which relates these three quantities: pressure, specific volume and temperature. And second information that we need to know is Cv as a function of temperature or Cp as a function of temperature. So, once we know the dependence of either of the specific heats on temperature, we can use any one of the relations. And also, as we have seen in our example problems, it is not generally required in a particular problem to make use of both the relations. We can always use the relationship between specific internal energy and specific enthalpy to calculate one from the other. Like for a certain problem, if suppose Cv is known to us and we have the PVT relationship, then we can use that to calculate the changes in internal energy, and then once we have this U2 minus U1 known to us, then we can easily calculate H2 minus H1 from there, invoking the relationship between U and H, that is H2 is U2 plus P2 V2, H1 is U1 plus P1 V1, that is it becomes U2 minus U1 plus P2 V2 minus P1 V1, that is corresponding flow works for both state 1 and 2. Or vice versa, in a certain problem, if suppose we are calculating this one, because we have Cp known to us, then we can easily use that to calculate U. And also which one, if we have information available related to both Cp and Cv, then which one to use, that depends upon exactly what we are trying to identify, and also sometimes depending upon what kind of process that we are dealing with. Like if suppose we are dealing with a constant volume process, an isochoric process, then for an isochoric process this term goes to 0. Therefore, du reduces simply to Cv dt, and it is much easier to operate with the relation for specific internal energy. Whereas, if you are dealing with a constant pressure process, for that this dP goes to 0. So, this entire bracketed term does not need any consideration. So, dH becomes just equal to Cp dt, and we can easily calculate the changes in enthalpy, and from there we can calculate the changes in internal energy. Similarly, we can calculate the changes in specific internal or specific entropy following a relation like this, where again we need the PVT relationship and also Cv as a function of temperature, or alternately we can have a different relation where we need to make use of the Cp relation as a function of temperature. So, we can use either of them in a given scenario. And if we want to know how Cp and Cv varies with temperature, then this is an example of relation of Cp with temperature. So, from the knowledge of again just the PVT relationship, we can easily calculate Cp as a function of temperature. And say if we want to perform one simple analysis, say for an ideal gas, to calculate the expression for Cv. We have already done in our previous module, I guess, but still suppose our relation is PV equal to RT. So, from there, from the known equation step, we can easily calculate this differential dou 2 V dou T2 from P is equal to whatever we get, and from there we can easily calculate Cp minus Cp naught corresponding to whatever temperature we are looking to identify. And finally, the Mayer relation, which gives us the relationship between Cp and Cv. So, these are the generalized relation that we have developed. These are applicable for any kind of thermodynamic system, any kind of process that they are undergoing, we can apply this particular relation. Also, two other thermodynamic potentials that we have used or we have defined earlier, the Helmholtz free energy and Gibbs free energy. Now, here we have defined or developed relation for changes in two of the thermodynamic potentials, the specific internal energy and specific enthalpy, because these two are the most common ones. But there may be certain situations where you are being asked to calculate the changes in specific Helmholtz energy. Then how you can go for this? Of course, you can again, that being quite similar to enthalpy being a combination property, you can simply use its definition. So, like suppose you are looking to calculate F2 minus F1, that is the changes in specific Helmholtz free energy during a particular process. Sometimes this is written as F12, which represents the change in value of F from 1 to 2. So, we know what will be your F2. F2 will be U2 minus T2S2 minus F1 will be U1 minus T1S1. Similarly, if you are looking to calculate the changes in specific Gibbs free energy, then G12, that is G2 minus G1, that will be equal to, from the definition of G, is H2 minus T2S2 minus H1 minus T1S1. Of course, we can still develop relationship something like dF equal to whatever or dG equal to whatever, but using the Maxwell's relation, but there is no need for this, because we can still just use the definition and use the changes in these properties as well. So, I am leaving one exercise for you. You please try to solve that exercise using the informations that I am providing you. Say for example, we are dealing with a system where helium is being used as the working substance. So, you are having helium as the working substance, which is following the equation of state in the form of P into V minus A equal to R T, where this A is equal to 0.001 0.01 meter cube per kg. So, this is the PVT relationship that is given to you, and it is said that the system is undergoing a change of state from 100 kPa 20 degree Celsius to 600 kPa 300 degree Celsius. So, state 1 corresponds to 100 kilopascal 20 degree Celsius, that is your P1 is 100 kilopascal, T1 is 20 degree Celsius or 293 Kelvin. Similarly, T2 is 300 degree Celsius or 573 Kelvin, and P2 is 600 kilopascal. So, you have PVT known, and then the value of this constant A is also given. So, from this you calculate the changes in all the corresponding thermodynamic potentials. That is, I am asking you to calculate the changes in specific internal energy, changes in specific enthalpy, changes in specific Gibbs free energy, and changes in changes in specific Helmholtz free energy and changes in Gibbs free energy, and in addition you also have to calculate the changes in specific entropy. I am intentionally have not provided the value of R and Cp or Cv in this case, that you have to identify from your textbooks. Using that, try to calculate this will be a good exercise for you to do, where you have to make use of the PVT relationship, make use of the relation for R and Cv or Cp, and also the relationship between the potentials, which I am sure you will be able to do this. Let us do a little bit of exercise of our own of a different kind. You have been asked to prove this particular relationship with making use of the Maxwell's equations. Here we do not need to bother about the relations for du or dh, we just have to use the Maxwell's relation to prove this. Now, for this let us make use of the Maxwell square. So, this is the Maxwell square you have, which involves all the 4 thermodynamic potentials and also the 4 parameters of our concern, that is pressure, temperature, specific volume and specific entropy. So, how can we use this particular relation, or how can we prove this particular relation? Let us go one by one. Let us take the left hand side. So, your left hand side is dou p dou t with constant S. Now, can we get this particular one from Maxwell's relation? P and T are there in the same horizontal line like this. However, S, the diagonal of P is V and not S. That means, we definitely do not have any Maxwell's relation which is directly applicable for this. Then how can we proceed this? Look carefully, P and S are not in diagonal to each other, but T and S they are at the diagonal. So, we shall be making use of something called the reciprocity, that is we are taking the inverse of this, or we are writing this as equal to dou t dou p of S whole to the power minus 1. Now, dou t dou p at S, is it there in the Maxwell's equations? It is there definitely, because T and S are opposite to each other and P is a neighbor to T. So, see the Maxwell square. So, what this one will be? Dou t dou p at S will become dou v dou S at P whole inverse, or again using the reciprocity we can write dou S dou v at P. So, we have converted this to some other form. Now, work on the right hand side. It is much more calculation involved in this. So, we have k upon k minus 1 into dou p dou t at V. Dou p dou t at V can be replaced using the Maxwell's relation. So, what can we do for this? Dou p dou t at V, and P and T again are neighbor and V is reciprocal to P. So, this will become dou S dou V at constant P. Am I right? Dou p dou t at constant V is becoming dou S dou V at constant T. That we can write, but before that we have to know what is this k parameter. I hope you know the definition of k, that is why I have directly gone for this, but k actually as per the standard thermodynamic notation, k is Cp upon Cv. So, k upon k minus 1 is Cp upon Cv divided by Cp upon Cv minus 1, that is it is Cp by Cp minus Cv, and Cp minus Cv we have developed in the previous lecture can be written as T into dou p dou t at constant V into dou v dou t at constant P. So, we have to make use of this here, and therefore, though we could have used the Maxwell's relation directly, that we are not doing here. What we are doing is we are putting this substitution for k. So, k by k minus 1 becomes Cp upon Cp minus Cv into dou p dou t at constant V, or replacing Cp minus Cv now using the relation we have to have Cp upon T remaining in the denominator into we have dou T dou P using the reciprocity into dou T dou V at P using dou P dou T at V. So, what substitution we can do now? Here we have used the reciprocity for the relationship Cp minus Cv. Now, dou T dou P at V and dou P dou T at V, so these two can cancel out, leaving us Cp by T into dou T dou V at P. Now, what kind of substitutions we can do here so that the right hand side becomes equal to the left hand side? Dou T dou V at V, is that available on the Maxwell square? That is definitely available, because you can see in the Maxwell square T and V are neighbor to each other and P is opposite to this, or P is actually is a neighbor to this. So, we can't get this from Maxwell's equation, but again here we can make use of the reciprocity, that is dou T dou V at P can be written as dou V dou T at P, inverse of that, and dou V dou T can be written as using Maxwell's relation as dou S dou P at constant T, inverse of that. So, accordingly this one becomes Cp by T into minus of dou P dou S, like this. So, what next? What is the next substitutions that we have to do with T constant? Now, what is your Cp upon T? What is the Cp upon T? If you can invoke one of the earlier relations that we have used while deriving the relation for changes in entropy, Cp upon T was identified to be dou S dou T at constant P. So, again these substitutions, see there are several ways we can substitute the relations, but some of the substitutions actually are not required. Here we are directly going to substitute what we have developed here, the relation for Cp upon T. So, it is dou S dou T at P into dou T dou V at P. So, if we combine them, we have dou S dou V at P. So, this is your left hand side, this is your right hand side, and they are equal to each other, which proves our relation. So, see the way I have developed this particular one. There are several ways we can substitute something, make use of the Maxwell's relation, but at least twice we actually use some substitutions and went into the opposite direction. Like this is some substitutions which was not required, another substitutions we used here by directly putting the Maxwell's relation, that was also not required. Rather, we have to make use of this Cp minus Cv relation, and we have to make use of this relation to prove whatever we are supposed to do. This way, using the Maxwell's relations and also using the generalized equation that we have developed, there are several other relations which can be proved, and they again have several applications in practice. Let us have another small problem. Here we have to prove something involving beta and alpha. So, let us try. What is your expression for alpha? Alpha is the isothermal compressibility, that is minus 1 upon V dou V dou P at T. So, here we have alpha into dou P dou T at constant V. So, if we put it, it is minus 1 upon V dou V dou P at T into dou P dou T at V. So, what should be the substitution that you can use here? Anything clicking in your mind? The cyclic relation. What will be a cyclic relation between PV and T? That will be dou V dou P at T into dou P dou T at V into dou T dou V at P equal to minus 1, something we have used. So, if we put it here, so we have minus 1 upon V, and this becomes, using reciprocity now, it becomes minus of dou V dou T at P, that is 1 upon V dou V dou T at P, which is nothing but beta. So, it is a very simple proof, that is beta is equal to alpha into dou P dou T at V. And these are numerous relations can be proved just using the definitions, is using some fundamental equations of partial differentials, and of course, the Maxwell's relations. These are a couple of good exercise to have, which I have shown here. Like the second one is quite straightforward, but from the first one we have seen how we can we may go in alternate direction, just trying to substitute something without understanding exactly where we are trying to go. I hope you have I am able to convey the way we can approach such kind of problems. Always try to prove or try to make use of the substitutions judicially, because there are several ways you can substitute the same variable, but in there may be situations where only one may give you the correct result. Let us now move to the discussion of couple of other concepts which are unrelated, but again very important and gives rise to very important thermodynamic applications. And the first one of them is the Joule-Thomson coefficient. The Joule-Thomson coefficient characterizes a throttling process. Now, what do you mean by throttling? When a fluid, a liquid or gaseous, is allowed to pass through a very small restriction, like flow across a valve or flow through a very small dimension tube like a capillary tube, then that kind of process is generally known as throttling. During the throttling process, there is no heat and work interaction involved, there is hardly any changes in kinetic and potential energies. However, there is significant change in the pressure. The outlet pressure commonly is much lower than the inlet pressure. Like the situation shown here, here a fluid is passing through a valve, it is coming at 800 kilopascal pressure and 20 degrees Celsius, and outlet side pressure or outlet pressure on the downstream of the valve is just 200 kilopascal. So, there is a significant reduction in the pressure. However, its temperature may be greater than 20 degrees Celsius, may be less than 20 degrees Celsius, or may remain equal to 20 degrees Celsius. That will depend upon the nature of the process, and which can be characterized by this Joule-Thomson coefficient. Before defining the Joule-Thomson coefficient, let us try to understand the thermodynamic nature of this particular process, and for that we have to apply the first law of thermodynamics on this particular process. So, let us assume it is a steady flow process where mass is coming with m dot 1 and the outlet mass is m dot 2. Now, under steady state, applying principle of mass conservation, we know that m dot 1 is equal to m dot 2, let us say equal to m dot. Now, we apply the first law of thermodynamics on this. So, the general expression, the change in the total energy content for the system, or the time rate of change of total energy content of the system will be equal to the amount of heat added to the system minus amount of work done by the system plus the amount of energy coming into the system in form of mass transfer coming in or going out. Now, in this particular case there is no heat transfer, there is no work transfer, and also we are talking about a steady flow system, that is energy content of the system is not changing with time. Therefore, we have summation of m dot I theta I is equal to 0. Now, there is only one inlet and one outlet for the system. So, we have m dot 1 theta 1 minus m dot 2 theta 2 is equal to 0. Here m dot 1 is positive because it is coming to the system, m dot 2 is going out of the system. So, that is negative, and m dot 1 and m dot 2 are equal to each other as per the mass conservation principle. So, we have theta 1 equal to theta 2. Now, if we expand this theta 1 and theta 2 in terms of their component, then what it will be? Theta 1 will be equal to the summation of corresponding kinetic energy plus corresponding potential energy plus enthalpy. Similarly, theta 2 will be half C2 square plus Gz2 plus corresponding enthalpy. Now, changes in kinetic and potential energies can virtually be neglected in this particular case, and therefore, what we are getting ultimately is H1 nearly equal to H2. That is, we are talking about a process during which the enthalpy remains constant, or we conventionally call that an isenthalpic process. So, a throttling process is an isenthalpic process during which the enthalpy of the fluid remains constant throughout the system or during the process. Now, we are therefore talking about an isenthalpic process during which there is a reduction in pressure, but temperature may increase or may decrease, and that is being expressed by this Joule-Thomson coefficient. Joule-Thomson coefficient is expressed by the symbol mu. Sometimes a subscript JT is added to signify that this is Joule-Thomson coefficient, because some properties like viscosity etc. are also given in terms of mu. So, this subscript JT is often put in to indicate that it is Joule-Thomson coefficient only. And the definition of Joule-Thomson coefficient is dou T dou P at constant H, that is the change in temperature with pressure for a constant enthalpy process. In a way you can say that it represents the slope of an isenthalpic line on the TP plane. That is, if we plot the process on a temperature pressure graph T here and P here, then and if this is a line during which enthalpy remains constant, that is along this line, suppose this is a starting point 1, this is the arrow, and this is the ending point 2, during which enthalpy remains constant, then the slope of this particular line is the Joule-Thomson coefficient. Now, during the throttling process, pressure is always decreasing, that is your dou P is negative. That means, if we are talking about your Joule-Thomson coefficient to be less than 0. What does that mean? We know that during the process pressure is decreasing, then this process to be this coefficient to be negative, temperature has to increase. So, a negative value of Joule-Thomson coefficient during the throttling process indicates an increase in temperature. If this is equal to 0, that means temperature remains constant or there is no change in temperature during the process. Whereas, when the Joule-Thomson coefficient positive, what does that indicate? Dou P is negative, then the coefficient can be positive only when dou T is also negative, that is temperature also decreases similar to pressure. And this magnitude of Joule-Thomson coefficient therefore gives us an idea exactly what kind of thermal effect that we are going to get. If your Joule-Thomson coefficient is negative, temperature at the outlet will be higher than temperature at the inlet, and therefore, we are going to get a heating effect. Whereas, when the Joule-Thomson coefficient is positive, temperature at the outlet will be lower than the temperature at inlet, and therefore, we are going to get a cooling effect or an application towards the refrigeration industry. So, when Joule-Thomson coefficient is negative, its application is heating effect, or when we want some room heating kind of application, we can go for this. However, if our target application is refrigeration industry, that is we want a cooling effect, then we have to ensure that the magnitude of Joule-Thomson coefficient is positive, that is then only we are going to get the cooling effect. So, the choice of choosing a refrigerant, we have to ensure that under the given circumstances the value of the Joule-Thomson coefficient is a positive one. Now, this discussion is for a particular enthalpy. Similarly, for every enthalpy or every given value of the inlet enthalpy, the nature of Joule-Thomson coefficient will show certain kind of trend, and that is what is shown here during this simple experiment. Here we are doing a particular experiment where we have taken a capillary tube just like this, where the inlet state is fixed, that is the fluid is supplied at a pressure P1 and T1, and outlet pressure is controlled. This P2 is the outlet pressure which is controlled. As the fluid is flowing through this restriction, it is losing some pressure, because for a given value of P2 the certain amount of pressure drop it is suffering, and outlet temperature will keep on varying with the choice of your outlet pressure, and therefore, this outlet temperature T2 can be higher than T1 or can be lesser than T1. Just look at the TP diagram that has been plotted here. This is the state from which we are starting and we are moving in this direction, that is pressure is reducing during the process. If our final state is somewhere here, then the temperature is higher, that is what is the value of your Joule-Thomson coefficient in this particular state. Here the value of your Joule-Thomson coefficient is negative, because pressure is decreasing but temperature is increasing. If pressure is decreased further, if we reach our state point somewhere like this, there is further increase in temperature, Joule-Thomson coefficient remains negative. If we continue this way, we reach this particular state where again temperature is higher, but the slope of the curve has started to flatten out. So, Joule-Thomson coefficient is still positive, sorry, still negative, but maybe its magnitude is approaching 0. And then somewhere here the curve becomes a flat one, that is it reaches the maximum possible temperature, we have some kind of inversion. At this particular point of inversion, there is no change in temperature with change in pressure, that is the value of the Joule-Thomson coefficient is equal to 0 at this point of inversion. If the pressure is reduced further, so that we reach this particular point, then you can see now there is a reduction in temperature, or temperature started to reduce, because now the Joule-Thomson coefficient has become positive. If we reach somewhere further here, there is a further reduction in temperature, and therefore, we can say on this particular side the Joule-Thomson coefficient is positive, that is reduction in pressure, temperature has also started to reduce. This is a constant enthalpy line, and if we divide this particular line into two zones, then we can see on this side Joule-Thomson coefficient is negative. So, if our operation is restricted to this right hand side, you are going to get a heating effect, whereas if we are operating on this side, then you are going to get a cooling effect. Our operation can be extended to the refrigeration industries, because the Joule-Thomson coefficient is positive. And this point of inversion or the point of maximum temperature is very important, because for the given value of this inlet enthalpy, we can, from the property of the fluid, we can identify the maximum possible temperature, and accordingly can identify the location of this inversion on this constant enthalpy curve. Here now, if we repeat the experiment for several such inlet states, this inlet state actually specifies your inlet enthalpy, which remains constant during the process. If we modify the inlet state, the value of the enthalpy also changes, and we are going to get a different line. This way we have got several lines by continuously increasing the enthalpy, and for all of them during the experiment we can see that the same nature is repeated. So, for the first line we are getting our inversion here, for the second line we are getting inversion here, for a third value of inlet enthalpy we are getting the inversion somewhere here. If we join all these inversion points, then the line that we get, that is called the inversion line. So, inversion line is basically the locus of all these inversion points corresponding to individual inlet enthalpy curves. And the point where this inversion line touches the vertical axis, that is the p equal to 0 situation. This line has the restriction or has the equation of p equal to 0. So, this temperature is known as the maximum inversion temperature. It is a characteristic of any fluid. When we are operating below the maximum inversion temperature, we can see that we can have both situations, Joule-Thomson coefficient greater than 0 or Joule-Thomson coefficient less than 0. Joule-Thomson coefficient less than 0 on the right hand side of your inversion line, and it is greater than 0 on the left hand side of the inversion line. However, if your operation is on the higher side of this maximum inversion temperature, then what we can get? Then the value of Joule-Thomson coefficient is always negative. You can never reach the zone where Joule-Thomson coefficient is greater than 0. That means, if your operation is happening at a temperature level above the maximum inversion temperature, then throttling is going to give you only the heating effect, but no cooling effect. Whereas, if your operation is restricted below the maximum inversion temperature, you can get both heating and cooling effect by choosing the outlet temperature and thereby modulating the value of this Joule-Thomson coefficient. It is as I have mentioned, this maximum inversion temperature is a property of the substance. For example, for substances like hydrogen, maximum inversion temperature is minus 68 degrees Celsius. That means, if we want to apply hydrogen for some kind of cooling process or refrigeration process, then first you have to reduce the temperature lower than this minus 68 degrees Celsius, and then only you can use hydrogen as a refrigerant. But if we are operating at the normal ambient condition, then there, as this temperature is higher than the maximum inversion temperature, so the Joule-Thomson coefficient for hydrogen will always be negative for any pressure level, and hence it can only give you the heating effect, but no cooling effect. Whereas, if you are operating at cryogenic levels, say at minus 150 degrees Celsius or something, hydrogen can also be used as a refrigerant. Most of the common synthetic refrigerants that we use in refrigeration industries or in air conditioning industries, they generally have maximum inversion temperature substantially higher than the ambient condition. and therefore, we generally do not need to bother about this. Finally, let us try to get some kind of mathematical criteria for the Joule-Thomson coefficient. We know that we are talking about an isenthalpic process. Now, this was the relation that we have developed earlier for changes in enthalpy. Then during the throttling process, enthalpy remains constant, hence this is equal to 0. So, let us reorient this to take dP on one side and dt on another side. That means, we can write Cp dt to be equal to T into dou v dou t at P minus V dP, that is dou t dou P at constant h, which is nothing but our Joule-Thomson coefficient. This becomes equal to 1 upon Cp into T into dou v dou t at P minus V. So, this way we can easily calculate the value of Joule-Thomson coefficient again from the knowledge of the PVT characteristic and the value of Cv for a given situation. As a final point, the magnitude of Joule-Thomson coefficient, I repeat, is very important in the HVAC industry particularly, that is what kind of application we are going for, a heating application or a cooling application. Your outcome or the choice of refrigerant will be depend upon the level of Joule-Thomson coefficient corresponding to that operating conditions. Let us do again a couple of small exercises to calculate the value of Joule-Thomson coefficient now, and for this we are again choosing an ideal gas PV equal to RT. Now, this is the expression for Joule-Thomson coefficient. So, to get this, let us get this dou v dou t first for this Joule-Thomson coefficient for this ideal gas. So, we have PV equal to RT, that is V is equal to RT upon P, that is dou v dou t at P becomes R upon P. So, if we put it here, minus 1 upon Cp to V minus RT by P minus 1 upon Cp, V minus what is RT upon P? It is V only, is equal to 0. That is Joule-Thomson coefficient for an ideal gas is 0, and that is logical only because we have proved in the previous class that for an ideal gas enthalpy is a sole function of temperature, pressure does not have any role. So, enthalpy of an ideal gas can change only when there is change in temperature, or vice versa. If enthalpy is constant, that means temperature is also constant, and during the isenthalpy, during the throttling process, as we are mentioning it to be isenthalpic, that is enthalpy remains constant, temperature also has to be constant, and hence we are getting a 0 value of the Joule-Thomson coefficient. Another case, here we have a more complicated, the van der Waals equation of state. We have to calculate the expression for the Joule-Thomson coefficient for this. So, same procedure, let us write this as V minus B equal to RT upon P plus A by V square, this V is equal to B plus RT upon P plus A by V square. So, if we differentiate this with respect to temperature, maintaining pressure constant, that is dou V dou T, P constant, what it will be? B and A are constant here. So, it becomes R into P plus A by V square minus RT into P is a constant here, A is also a constant. So, we have minus 2A V to the power minus 3 into dou V dou T at constant P divided by P plus A upon V square whole square, or if we simplify this, then we have P plus A upon V square whole square into dou V dou T at P is equal to P plus A upon V square plus 2A R T upon V cube to dou V dou T at P, or dou V dou T at P becomes equal to P plus A upon V square into R divided by P plus A upon V square whole square minus 2A R T upon V cube, and therefore, the expression for the Joule-Thomson coefficient mu Joule-Thomson becomes equal to 1 upon Cp into P plus A upon V square into RT divided by P plus A upon V square whole square 2A RT upon V cube minus small v. This is a quite complicated expression. Now, you can simplify this in whatever way you want this, and once we have the given information available, that is we are talking about a particular state point, you know the expressions for the pressure, temperature, etc. Putting this, you can calculate the value of the Joule-Thomson coefficient. So, that is the concept of the Joule-Thomson coefficient. Let us quickly move on to discuss the final concept in this particular module, which is of the Clapeyron equation. Clapeyron equation is the application of the Maxwell's relation during a phase change process. It can be any kind of phase change process, liquid to vapor, solid to liquid, or solid to vapor, or vice versa, but the Clapeyron relation provides us a generalized platform of calculating the changes in entropy and changes in enthalpy during a phase change process. Now, this is one of the Maxwell's relation that we have developed in the very first lecture of this module. When you are talking about a phase change process, then we know that the saturation pressure is a function of temperature alone. That is, during the phase change process, the pressure is a sole function of temperature, and therefore, we can, instead of using the partial differential notation, we can write this just dp dt saturation, which actually represents the slope of the saturation curve on a pressure temperature plane, and that is equal to dou S dou V at T, or if we separate them out, that is dou S becomes equal to dp dt saturation into dou V, integrating this, say from state point 1 to 2, where state point 1 indicates the starting point of the phase change or starting state of the phase change, where we have only the first phase available, and point 2 refers to the exactly the finishing point of the phase change, where we have the second phase available. Like if you are talking about a liquid vapor phase change process, then phase 1 refers to 100% liquid, which is just about to vaporize, about to start the phase change, and point 2 refers to 100% vapor state, where the phase change has just completed. So, we can then write this as S2 minus S1, which as per our notation is S12, is equal to dp sat, because this does not represent depends on the volume, it as V2 minus V1, or the changes in the slope of the curve can be written as S12 by V12. This is a typical saturation curve on PT diagram. This is actually a curve which corresponds to all the three processes. I shall be coming to this curve, reviewing this curve in as a part of the next module, in the very first lecture of the next module. But here this third curve represents your saturation curve, and dp dt saturation or dou P dou T saturation, which actually is a constant at given temperature, it represents the slope of this particular curve. This is what we are referring to. Now, if we are talking about, or if we are our objective is to calculate the changes in entropy, we can easily do this. How we can do this? means let me just rearrange it. So, S12 is V12 into dP dt saturation. Say for example, we do the experiment for quite a few different temperature levels. Say at a temperature of 100 degree Celsius, we measure the corresponding pressure, then that gives us 1 point somewhere on this curve. Then at a temperature of 105 degree Celsius, we again allow the water to change its phase, then measure corresponding pressure. Then we do the experiment at 110 degree Celsius and again measure the corresponding pressure. This way we can get a few points of the curve, and then combining these points we can calculate the slope of this curve. And now suppose our objective is to do this calculation at T equal to 105 degree Celsius. Then at 105 degree Celsius, starting from phase 1, that is 100% liquid which is about to vaporize, going to phase 2 which is 100% vapor, just finish the vaporization, we can easily calculate the change in volume, thereby knowing this second term. So, once we know both of them, then we can easily calculate the change in entropy during this particular phase change process. And if we want to calculate the change in enthalpy, we have to make use of the TdS relation. What will be a TdS relation? We know that dH is equal to TdS plus VdP. Now, when the phase change process is going on, that is from liquid to vapor or any similar phase change process, we know that both pressure and temperature remains constant, that is dP goes to 0 and temperature remains constant. So, if we integrate this one over the phase change process now, then this is your H12, that is H2 minus H1, change in enthalpy over the phase change, is equal to T into S12, that is your H12 is equal to the saturation temperature into S12, or invoking the earlier relation, saturation temperature into V12 into the slope of the saturation curve. Or if our interest is to know the saturation curve or expression for the saturation curve, then we can also write, that is dP dt saturation is equal to H12 by T sat into V12. This particular relation or its alternate version is known as the Clapeyron equation, which allows us to calculate the change in enthalpy and consequently the change in entropy during a phase change process using the knowledge of the slope of the curve, the measurement of the saturation temperature, and also the measurement of the change in specific volume during this process. It is a very important relation. More application of it can be applied to any kind of phase change process. We just need to know the slope of the curve properly, which of course is complicated, but more on the nature of this curve we shall be learning as a part of the next module. An alternate version or an approximate version of the Clapeyron relation is sometimes used to know the saturation pressure, which is called the Clapeyron-Clausius equation. If we are talking about a situation of very low pressure, as the pressure keeps on decreasing, then the pressure of the vapor phase, particularly if we are talking about the liquid vapor phase change process, this Clapeyron-Clausius equation is particularly applicable to liquid vapor phase change. Now, when we are talking about very low pressure, then this V2 is extremely high compared to V1, such that the V12, that is equal to V2 minus V1, can approximate it as simply as V2. And we can sometimes assume this one at low pressure again as an ideal gas. As the pressure keeps on approaching the absolute zero pressure, the behavior of vapor also approaches that of an ideal gas, and therefore, we can approximate this by the ideal gas equation, which is R into the saturation temperature by the corresponding saturation pressure, or if we just drop the subscript, just R T by P. So, if we now invoke the Clapeyron equation, where we had dP dt saturation to be equal to H12 by T sat into V12, then using this approximation at low pressure, this now becomes V12 we are replacing. So, we have R into T sat square and we have P sat into H12, or if we rearrange the terms now, we have dP by P sat to be equal to H12 by R into d of T sat by T sat square. If we integrate this entire thing, say for two different saturation point, which is 1 and 2, where 1 refers to one particular saturation state, 2 refers to a different saturation state which correspond to a different saturation pressure and temperature, but they are reasonably close to each other, so that we can make use of this low pressure assumption. If this 1 and 2 are again reasonably close to each other, then this H12 can be approximately taken to be a constant. Then this becomes log of P sat at the second level minus P sat at the first level to be equal to, or I should say approximately equal to, because H12 we are assuming to be a constant, by R into 1 by T sat 1 square, square is dropped out because of integration, minus 1 by T sat 2. This particular equation is known as the Clapeyron-Clausius equation, which allows us to calculate the changes in saturation pressure from the knowledge of the changes in saturation temperature. You just need to know the corresponding enthalpy or change in enthalpy during the phase change, and also the value of this R. We shall be finishing off by doing a small numerical example, which will allow us to understand the use of this Clapeyron-Clausius equation. So, here is my problem. We have to estimate the saturation pressure of R134a, which is a refrigerant, at minus 45 degree Celsius using the data available corresponding to minus 40 degree Celsius, and these are the data. The value of R is given, H12 at minus 40 degree Celsius has been measured, and the saturation pressure at minus 40 degree Celsius has also been measured, and therefore, our T sat 1 is minus 40 degree Celsius. So, we can say minus 40 plus 273.15, which gives us 223.15 Kelvin. And the second point for which we are looking to do the calculation, the temperature is minus 45 degree Celsius. So, minus 45 plus 273.15, that is 228.15 Kelvin. The known saturation pressure, that is P sat 1 corresponding to minus 40 degree Celsius, here is 51.25 kPa, that is 51.25 into 10 cube Pascal. I would always suggest convert everything to basic SI unit, so that there is less chance of making any mistake with the units. Here R is given is as 81.49 joule per kg Kelvin. So, that is given in basic SI unit. However, there is a kilo factor in H12. So, this one can be written as 225.86 into 10 cube joule per kg. So, now we have to make use of the Clausius Clapeyron equation, and therefore, as the one we have just developed, P sat 2 1 is equal to H12 by R 1 by T sat 1 by T sat 2. So, your H12 is 225.86 into 10 cube divided by R is 81.49 into 1 by T saturation 1 is 223.15 minus 1 by 228.15, and you have to put the expression for P sat 1. If you put that, saturation pressure correspond the second saturation pressure, that is your P sat corresponding to minus 45 degree Celsius of saturation temperature, will be coming to be something like 39.48 kilopascal, which is the desired result that we are looking for. So, this way, using the Clapeyron equation and then its approximate version in the form of Clapeyron-Clausius relation, we can calculate the saturation properties of any fluid easily. And while the Clapeyron equation is applicable for any kind of phase change process, Clausius-Clapeyron relation is generally restricted to liquid vapor phase change only. So, that takes us to the end of our second module, where we have focused on developing generalized relations for changes in most important thermodynamic properties. So, we started with the mathematical perspective property. We understood how to understand whether a parameter z is a property or not once we know that it is a function of x and y and both x and y are properties. Then we discussed about the 4 possible thermodynamic potentials, the specific internal energy, specific enthalpy, specific Gibbs free energy and specific Helmholtz free energy. Then we derived the Maxwell's relations, 4 Maxwell's relations from the definition of these 4 thermodynamic potentials. We have also understood the Maxwell's square, and which is an ad hoc way of remembering this Maxwell's relations and corresponding TdS relations. Then we have developed generalized relations for 3 most important thermodynamic properties, that is U, H and S. And then we went on to derive the generalized relation for changes in specific heat or both the specific heats Cp and Cv and their relation in form of the Mayer relation. Then we have seen several kinds of application of each of these relations in different problems, like we can define new properties in the form of volume expansivity and isothermal compressibility. We can develop different relations between properties, and different other kind of suitable forms can be developed. And today we have discussed the concept of Joule-Thomson coefficient, which is very important regarding the choice of a fluid for heating or refrigeration applications. And finally, we discussed about the Clapeyron equation, which has its application in the phase change processes in order to understand the changes in specific enthalpy and specific entropy during a phase change process, and also sometimes to calculate the saturation pressure for a given saturation temperature using the values at some other point. So, all these are actually the application of the Maxwell's relations, which allows us to perform thermodynamic analysis in a much easier pattern. So, that takes us to the end of module number 2. I hope you have understood the discussion that we had, because I have tried to develop all the relations here. If you have any confusion, first try to develop the relations on your own, listen to the lecture once more, may refer to the textbooks, and if still there is doubt, please write to me, I shall be very happy to help. So, the assignment will be online along with this video. You please try to solve the assignments, and maybe some additional problems you referring to the standard textbook, so that you grasp the concept properly. So, next week we shall be again back discussing about the properties of pure substances. Till then, take care.